All right, start with what is extraction. I'm sure many of you guys have done extraction before in for some extent. I'll give you some example right here. So making tea, like put a tea bag into a hot water, that's a form of extraction. What? Because things are coming out from a tea bag. Do you know what those things are? Well, color for sure, something that like show the color, and for sure, caffeine. Oh, we all love caffeine. Yeah. All right, look at the definition. So extraction is a separation technique of a substance based on its solubility in one phase over the other. Okay. Caffeine soluble in water better than just like stay as a solid in tea leaf. Okay, that's why we can do extraction. This one we call solid liquid extraction. Another very familiar example is vanillin. Okay, vanillin also is organic soluble, which means it can soluble in some organic solvent, like usually polar organic solvent. So if you put vanilla into, let's say, organic solvent like ethanol, let it sit for a while. Um, the ethanol molecules can form interaction. We have hydrogen bond. This is hydrogen bond, hydrogen bond, hydrogen bond. Okay, so pull vanillin, this compound, out of the out of the leaf, and over time you're gonna see it get darker, darker, and darker, and that's how we make ice cream. Yay! So that's a solid liquid extraction. In the lab, you're going to do liquid extraction, which is a separation technique based on relative solubility between two immiscible liquid. Okay, I'll give you some example right here. Liquid right here. So caffeine, that's a structure. We all love caffeine. Like a lot of us drink a lot of caffeine, and maybe some of us have caffeine addiction. Yay! Anyway, caffeine somewhat soluble in water. If we have 100 milliliter of water at 20 degrees, we can dissolve 2 grams of caffeine. Not soluble as well, but I mean it's soluble some. Okay, in the coffee we have like how many milligrams? 20 milligrams, something like that. All right. Anyway, let's say you have a water and you got caffeine in it. Other dots right here. I put about 10 dots in here. Okay, and then I'm going to add dichloromethane. If you remember from the previous video, dichloromethane is immiscible with water. They form 2 layers. Is at the top or at the bottom though? What's the density? It's heavier. It's denser than water. So the dichloromethane will form the bottom layer. Look like that. All right. We have organic layer down here and an aqueous layer up there. All right? If you put the stopper on and then you shake it, this is gonna happen. The caffeine molecules will migrate from water to the DCM layer. Okay, but here's what happened. Right, if you do the same thing with diethyl ether, all right, we have diethyl ether point here. If you remember, diethyl ether is also immiscible with water. We don't form top or bottom layer. If you remember, it's less dense than water. They form at the top. Okay, put the stopper in, we shake it, and this is what happened. Doesn't go as well. Doesn't go as well. Like, now the question is, if you want to do extraction, because extraction we rely on the relative solubility, right, of the compound between 2 layers. Now, what's so when we have to pick, and how do we know? Well, chemists come up with the we call distribution or partition coefficient. It tells you what phase the compounds favor. For example, the partition coefficient of caffeine, this caffeine, in DCM over water is 9.9. So basically, if you do like make an easier math, so 99 over 10. So most of caffeine favor the DCM layer. All right. But now, the partition coefficient of diethyl ether in water is 85 per 1,000. So caffeine prefer to stay in water rather than diethyl ether. Okay. In this case, for extraction of caffeine, we use DCM. All right. So we have partition coefficient. Okay. All right. Anywho, let's guess right here. Okay. Let's say I have 2 layers, so diethyl ether and water, and then I add benzoic acid into that separatory funnel. All right. Now I give you partition coefficient. Question is, which layer benzoic acid will go to? Is it the organic layer or aqueous layer? If you look at the partition coefficient, so benzoic acid favor diethyl ether 10 to 1 ratio. Okay, so most benzoic acid is going to go up to at the top, organic layer. All right, now try this one. All right, let's say I have sodium chloride. All right, sodium chloride is ionic bond. Now, which layer the sodium chloride favor? Totally water. Ionic bond, oh come on. So with water soluble, water soluble from ion dipole, really strong intermolecular forces. All right, so sodium chloride will go to the bottom, to water layer. All right, try sodium benzoate. Which layer do you think it will go? Organic layer or aqueous layer? If you spot right here, ionic bond, of course, will form ion dipole interaction with water, really strong intermolecular interactions. Of course, any salt like sodium chloride, sodium bromide, like salt like this, sodium benzoate you saw earlier, most of the time they go to water layer because the charged compound favor the ion dipole interaction. Okay, all right, benzoic acid right here. So we saw earlier that it favors diethyl ether rather than water. Okay, now we're gonna play with solubility. Look right here. This is really the heart and soul of this lab. I'm going to add 1 molar sodium hydroxide. Okay, just add onto it. What's going to happen? Well, I have hydroxide around in here. Shake it. We have a base. We have an acid. Of course, you guys know acid and base, they react, right? Hydroxide will go take away that proton. Benzoic acid will turn to be benzoate. Guess what happened to solubility? This guy turned to be a salt charged compound. And you guys know which layer, aqueous layer or organic layer, the charged compound favor. Totally. If this guy would go down to water layer, that's how we play with solubility. You see that? All right. From what you just saw, try this one. I have a mixture of aspirin and vitamin D. Okay, both of these favor diethyl ether. Vitamin D is a fat soluble compound, totally not in water, right? Aspirin look like this. Right? Also favor organic layer. I want to separate these two. You get you get a mixture of aspirin and vitamin D. How do you separate these two? Using extraction. Well, some of you might realize that aspirin, look at the structure of aspirin. So we have arine, we have an ester group, we have a carboxylic acid group. The carboxylic acid right here, we can play the solubility by doing this. If this guy were an acid, what if we remove this proton? This guy turned to be an ion. And when it becomes an ion, we'll soluble in water, right? So this is what we're going to do. We're going to add a base, like usually a weak base, sodium bicarbonate solution, add on to it. Okay, so we have, all right, this is what's going to happen. The hydroxide that come from the base that we just added, we go take away the proton. Well, base and acid, they react. And we're going to end up with a charged compound. And you guys know the charged compound favor water layer. And that's how you separate them, you know? In real life, let's say in the lab, this is what's going to happen, right? So let's say you have the carboxylate right here, aspirin with a negative charge, so favor the water layer. So you're going to drain the bottom layer. All right. Now here's the thing. The species down here in water layer is still not the aspirin, right? So it looked like that. Well, what do you have to do? If I want to make this guy turn back to aspirin, what do we have to do? Just add proton onto it. What species, what reagent that allow us to add proton back onto this compound? An acid, add 1 molar hydrochloric acid, so it's just acid-base reaction, and you get aspirin back. Okay, but here's the thing, a little bit detail in here. This guy, right? This guy is soluble in water, but aspirin is not as soluble in water. But right now, this guy is actually in water. What's going to happen? It's amazing. You're going to see precipitation just like that, quick. You're not going to see this in anywhere else, right? Only in chemistry. It's going to precipitate right away. You see, oh, that's when it came out. It tells you, hey, you actually get the aspirin, the neutral aspirin. Okay? So that's how we do it. Basically, you can play the solubility, right? So we have an acidic functional group at a base. It moved to water layer because of the charge. And you can do reverse the process by adding an acid. And if you have a basic functional group like amine, you can add an acid, add a charge onto it. It's going to go to the water layer. And at a base, you go back in the same way. Okay? All right, so that's a theory behind extraction and acid-base extraction. Now we're going to use that in the lab. Let's talk about what we'll be doing in the lab. Okay, next video.